Okay, thanks. So my name is Zhasil, and I work as a senior observability engineer at PriceFX. And today we are going to talk about statistics in observability and how the statistics can help us with anomaly detection. So why to bother at all? Well, I'm still considering myself a developer first, even though it's not my main focus anymore. But I just like to find solution to a problem, make something new. How many of you likes to create something new, find some new solution? Okay, that's quite a lot. And how many of you likes to meet in afterwards and look for all those hard to reproduce issues? No one. That's everyone. Uh, yeah, we have it the same, and we want to make our lives a little bit easier, so you can focus on the fun part and not on the bug hunting. At PriceFX, we have clients all over the world, providing platform that supports full pricing lifecycle. That means our platform needs to be really robust and stable. So we looked how to make our lives a little bit easier. We wanted to tackle complaints like it's slow or it behaves funny every other weekend. In general, we wanted to be able to solve issues that are hard to replicate without any concrete error. So we went for the anomaly detection with statistics, and I'm really bad at math, especially when the numbers are replaced by the alphabet. So I was an obvious choice to delve into statistics and all those equations hidden in there. So what did we want to get from the statistics at the first place? We wanted to detect anomalies and have alerts for them. Anomaly is everything out of the ordinary, like spike or decrease in memory consumption. Trend, prediction, and seasonality can show us overall direction that we are taking, example in resource consumption, but also day-to-day ups and downs, and with that help us with scaling. Pattern comparison serves to compare detailed baselines from point of time, so we can compare what, if anything, changed with the new release. For most of our needs, we needed just two statistic methods, luckily. First one is STL, which is a very precise aggravation for seasonal trend decomposition using loess. And this method lets us to see a repeating pattern and trend. Trend is a long-term direction that ignores day-to-day fluctuations, captures just the overall situation. And seasonality is the repeating pattern. Imagine morning and afternoon traffic jams and the more or less calm situation in between. For better explanation, trend will tell you there are more cars on the roads every day. Seasonality will tell you that you can meet most of them at 7 a.m. in the traffic. And then there is a residuum, which is nicely omitted in the name. And the residuum which was left after the trend and the seasonality is subtracted from the raw data. Fluctuations in the residuum can indicate anomalies or overall stability of your system. Because traffic jam every day in the morning is not nice, but it's something stable. Random traffic jams during the day are some instability. So this is how it looks. It's one of our pre-production instances that calculates data. It does the same calculations with different data sets over and over and over. And with this decomposition, we can see the trend, which is the yellow line. And we see that it has some increases during the week until it's stable and then decreases a bit for a weekend. We have seasonality in blue, and we can see that, each evening it goes up as automating jobs are taking place. And there is a decrease as customers take over to process data and go home after shift. And we see the orange residuum, which pretty much follows the same pattern as our system is quite stable. The red line is a baseline with 1 month offset from the actual data. The actual data would be green, but as our system and workload is stable, the red covers the green entirely. The second method is rolling z-score. It's our main driver for detecting anomalies. Z-score is measures deviation from average. As in previous example, it will be shown against an environment that is recalculating prices, the same equations over and over with different data set, which seems pretty stable, as we just saw, until it's not. And in the example, there is the very first anomaly we ever caught. So as I said, the z-score is our main anomaly detector, it calculates deviation from average over a specified time period. It's computed as a current, which is the raw data, minus average divided by standard deviation. Z-score is number of standard deviations from the mean. And it's measured as an absolute number. 68% of measurements are within the absolute threshold of 1. 95% goes up to threshold of 2. And 99.7% of situations are stopped at 3. So if you are up to threshold of 2, you are okay. Between 2 and 3, if it's not long term, you are still somewhat okay. Above 3, there is a problem. And this is how it looks. We have the green area up to 2, which is okay. The yellowish, probably, is be alert, but you are still okay. And above, there is a danger, there is an anomaly. And as you can see, there is an anomaly. The whole week seems pretty stable. Applications computing data, everything is okay, up to the very last day, where resource consumptions go up to 6, and remember, 3 covers 99.7% of all cases. So something definitely happened that should be investigated. And so we went to investigate, and we see that the application is fine, nothing fails, all computations are going. And in fact, a colleague of mine was just copying instance to another Kubernetes cluster. There were enough resources for that, but the average changed drastically, and it with the load. And that's a really important lesson with anomalies. Not all anomalies are exceptions. It just means that the status quo changed, and it's quite often wanted change. So how do we get to those nice charts, and what do we learn during the process? At the very beginning, we took data from the whole customer cluster. Customer cluster in our situation means all of our components dedicated to a customer, front end, back end, jobs that have their designated pods, database, and so on, all packed in one neat package. And we created detailed and quite complex recording rules for Prometheus. And to have some actual data, we put it into one of our pre-production environments. And this is how it went. Prometheus went down on lack of memory and could not restart, as it was unable to unpack and read all the data in there because of lack of memory. Our pre-production is used quite heavily by our customers, and we just lost entirety of monitoring in there. Very nice situation. And not just on the single environment, because we are very cool, we have pipelines, and the faulty rules were propagated by the pipelines to all of our pre-production environments. So for the fix, or even before the actual fix, we needed to pump up memory for Prometheus quite a bit, and that showed really nicely on our monthly bill. And the actual fix was using Thanos compactor. Compactor keeps the data out of Prometheus in its own storage. And then we did really massive rule planning. Basically, we kept just the most simple basic rules that we could have and let actually Grafana do all the counting. And now we have statistics for databases, for those customer clusters, which is all the instances, for errors in our logs, how many errors we have, each application component, nodes where it's running, the Kubernetes nodes, and for those jobs, which are dedicated pods. And we have several months of data. And the moral of the story is use the simple rules, just select the basic data at some reasonable rate, like 5 minutes, and use compactor, because statistics, at least in our situation, are based on averages. And compactor just further averages the data as the time progresses. And in a real-life scenario, you never need to know what happened at 9:30 in the morning on this day last year. You just need some general information, what was happening back there. So the STL and the rolling Z-score are our main drivers for the anomaly detection and for monitoring how our system behaves. But we added 2 more methods or charts for further insight. We have pattern comparison that let us compare current baseline with the selected time in the past. And so we can see how development changes affects our environment. And we have prediction, which is kind of mixed between seasonality and trend. And with that, we have a better insight of what's happening and how our system behaves. So this is the pattern comparison. This shows baselines over the last few weeks, and we can see how the system reacts to changes. And in fact, we can see some bigger difference on the baseline that's marked 7 days ago. But otherwise, it looks pretty much the same, which means our system is stable. We did nothing except for that one day. And I happen to know that on that day, we did some maintenance, which accounts for the discrepancy. Otherwise, it would be your timeline and your clue that something was amiss that needs further investigation. And this is the prediction chart that shows CPU usage on one of our customer clusters, which is all of those components dedicated to a single customer packed together. And the prediction is actually average over the last 3 weeks. The average should smooth or flatten day-to-day bumps and show us how our application behaves. So we can actually see that in our environment, CPU usage is actually at its peak during the weekend, because that's where those automated jobs crunch most of the data, as there are no customers on the system that would need some response or somehow slow it down. And also the customers on the data prepared and application responsive as much during their working hours. So that was our implementation and what we gained during the process. Let's start with some general tips, because people tend to see what is just before them, not looking at the big picture, focusing on just their area of expertise. And this is really bad with anomaly exception, because anomaly is anything that goes from the ordinary, from the average, and you just need to know what's happening around you, because otherwise you will be overwhelmed by false alarms chasing ghosts. Because most of anomalies will and can or will be produced by normal wanting changes, normal releases, maintenance, and so on. Also, we are going through some drastic changes in our environment. You often change your infrastructure. You have short release cycle with massive changes in releases, which is typical for early stages of development. Then long-time measurements won't be that useful for you because you are just changing the baseline, the average, too often, so you won't have sensible baseline. And on the more technical side, apply for the anomaly detection the recording rules, keep them simple, save the bare bones of what you need. Make sure that you are collecting data long enough, because recording rules are not calculating backwards, which was a bad surprise for me. And you get them from the time you apply the rules onwards. So if you want to see what happens during Christmas season next year and compare it with this season, you need to start right now. And really use the compactor. You will get there tons of data really quick. And you just need to keep them in check. And further back you go in time, the less detailed the data you need. If there is some key message I would like for everyone to remember about anomalies, is that anomaly is not an error, it's something out of the average. For example, you have a database that lacks memory, so it swaps to disk. Your customer complains, it's slow. Yeah, obviously it's slow because disk reads are slow. So you fix the issue by adding more RAM to the database, and everything is okay. No more swapping, customer is happy, everything's smooth. Congratulations, you just created 2 anomalies. Disk and memory, because your disk usage went down and your memory consumption just increased. And that's all. So try the anomaly detection for yourself. And if you have any questions, contact me on LinkedIn, or we can grab some coffee out in the hall. Thank you for your attention.
Thank you very much. Actually, we have one question here. I know from whom, because he signed himself. So have you set up alerts for at least some rules, or there is too many false positive anomalies?
Yeah, actually, we are going for some time now with a big alerting refactor, because as we are quite robust, we have many teams and many alerting methods. So now I created some alerts just as proof of concept. The system is stable, which is okay for us, but we did not put them in production until the alert, the refactoring, or how to name it, will be completed.
Sounds good.
Yeah.
Okay. So thank you very much. Thank you for your talk and see you.